Hello everyone, my name is Derek. Today, I'd like to present our work entitled Implicit Rendezvous for Robotic Exploration Teams under Sparse Intermittent Connectivity, in short, IR². IR² is a general deep reinforcement learning framework that achieves efficient multi-robot exploration while respecting communication constraints. It has the ability to balance the longer-term trade-offs between disconnection for exploration and reconnection for information exchange. So, why this work, and how did we achieve this? Coordinated multi-robot systems are highly effective for large-scale exploration. It is important to consider the communication constraints between robots during the exploration process. For example, underwater exploration, where there's low transmission throughput, planetary exploration, where there are many corners and turns, and search and rescue operations, where there are many thick obstacles that hinders information exchange. It is therefore important to define realistic communication constraints that determines the connectivity between robots. In short, robots are required to balance between disconnection and reconnection. On the right, you can see an example of 3 robots exploring an unknown indoor environment. Here, you will observe robots disconnecting shown by red circles and reconnecting shown by green circles. We summarize the existing research work into 3 types of connectivity strategies. First, opportunistic connectivity, where robots meet and share information purely by chance. However, this introduces high-performance variance. Secondly, continuous connectivity, where robots continuously reconfigure their formation to remain connected while they explore the unknown environment. However, this sacrifices efficiency as robots are often not well distributed. Lastly, recurrent connectivity, where robots strategically disconnect and reconnect. If done well, this method can achieve efficient distribution and timely information exchange. Our work focuses on this type of approach. We formulate our problem as a generation of a set of path trajectories for all robots to fully explore the unknown bounded environment in the shortest distance possible. In our work, we define 2 different communication modalities. First, the proximity model, where robots are connected when the equivalent distance between them are sufficiently small. Second, the signal strength model, where robots are connected when the received signal power is larger than a specified threshold value. We model the decay of signal strength through the concept of path loss, which is the amount of signal strength attenuation when passing through different mediums. We present a general deep reinforcement learning exploration framework that balances the longer-term trade-offs between disconnection and reconnection. Our contributions are threefold. First, we made use of attention-based neural network with curriculum learning to help balance the above-mentioned trade-offs. Second, we employ a hierarchical graph formulation to achieve scalability to large-scale environments. Lastly, we validated the use of a single train policy that is generalizable to complex simulations and real-world environments. We split our approach into 2 key stages. First, the hierarchical graph formulation, where we aggregate all robots' sparse graph whenever they are connected. Second, the attention-based neural network, which inputs the combined graphs and outputs a policy on where the robot should go to next. The goal of this graph formulation is to obtain a sparse graph representation to prune the action space for efficient exploration. First, we generate a dense graph around the robot's position. Second, we generate a sparse global graph, which provides additional offshoot towards frontiers, also known as the division between known and unknown areas. Third, whenever robots meet, we can merge and combine their graphs, and finally sparsify the combined graph. Last, we prune the uninformative graph branches that does not lead to frontiers. Next, the encoder encodes the exploration graph into a multi-scale representation using stacked self-attention blocks. This allows for the capturing of long-term dependencies from the current node and accepts arbitrary graph structures given different kinds of exploration maps. Lastly, the decoder outputs the next location for the robot to explore. For our training, we make use of the combined graph, augmented with additional information. Such additional information include the graph node positions, exploration utility, which is the number of observable frontiers from each node, route history, other robots' positions, and the map surplus utility. In short, this utility comprises of the A-star paths between the current robot and all other robots' position. They are weighted by the robot's perceived map information surplus it thinks it possesses over other robots. The action generated is from a stochastic policy chosen from k nearest neighbors. The reward function, encourages exploration based on discovered frontiers, penalizes distance traveled, encourages backtracking along map surplus A-star paths, and completion rewards for fully exploring the environment. To learn intelligent recurrent connectivity strategies, we subject all robots to increasingly difficult environments with varying frequency and duration of this connectivity. We split our maps into 4 types: simple, corridor, hybrid, and complex. We train our policy in 2 stages, each with different map ratios. We validated our simulation with 100 randomly generated maps for each map categories. Our results indicate that curriculum learning significantly improves performance in complex environment. Here's a simple visualization of our trained policy with recurrent connectivity strategies in a complex map environment. On the right, you can see robots' own map belief, and on the left, you can see the combined overview of the exploration status that is not present to the robots during inference. To further validate our work, we employ IR² in 3 large-scale environments. These environments can go up to 340 by 340 meters in size. We employ 4-wheel drive robots with 3D lidars. We conduct experiments with 2 to 6 robots, repeating 3 times per experiment. We benchmark our work against 2 baselines. First, against a pursuit-based approach, where robots decide which other robots to pursue based on distance, cost of deviating from path, and exploration benefits of information sharing. Second, against a pre-planned approach, where robots agree beforehand on exploration budget and rendezvous location. Here, you can visually compare the performance of IR² against our baselines in an indoor environment. Once again, the red circle denotes a state of disconnectivity, while the green circle denotes a state of connectivity. We observe the IR² exhibits the least trajectory overlap and backtracking, followed by pursuit, and finally pre-planned. This is reflected by IR²'s distance and volume efficiency compared to the other baselines. Our experiments indicate that IR² generally outperforms our baseline by at least 6.6 to 34.1% in terms of distance efficiency. Admittedly, our approach sometimes performs poorer than pursuit in time efficiency, one main reason being the difference in programming language. We compare our work against our baseline in forest environment, and finally in campus environment as well. Lastly, we validated the performance of 3-row robots in a 25 by 10 meter maze environment. As you can see, each robot runs their own fully decentralized policy. We notice the intermittent disconnection and reconnection for robots to achieve efficient exploration. Here's the final merged sparse graph from each robot's belief, along with the path trajectories. In summary, we present a general exploration framework that uses deep reinforcement learning to train efficient recurrent connectivity strategies. Our work can be distilled into the 3 main contributions. We would like to acknowledge everyone that have contributed to the success of this paper. Feel free to check out our paper and open source code through the QR code provided. Thank you for your time.